So far in our discussion of magnetism, we have always talked about electrons as if or spins as if they are localized in space inside the crystal lattice. So, all our treatment has been under the assumption that the spins which are responsible for the magnetic behavior are all localized in space and stay fixed in a particular point of space for all time. We know that this assumption is not justified in the case of metals, in which conduction electrons in metals are somewhat free to move around, and so they are not fixed in space. So, this assumption is certainly not justified when discussing the magnetism due to spins which are in metals. So, if you want to discuss magnetic behavior of metallic systems, we have to have a different approach. The assumption breaks down of a fixed position in space, and therefore, we have to allow for this in our discussion. So, this is what we will do today, and we will find that very interesting effects take place when we do this. So, the main contribution to paramagnetism, let us discuss paramagnetism first, is from the free electron spin magnetic moment. Free electron spin associated with the spin angular momentum, there is a magnetic moment, and we know this magnetic moment is given by we write a negative sign to show that it is electron, and where here this is the g due to free spin, and g is known to be very close to 2. It is the Landau g factor, and therefore, we can write the magnetic moment as so that is the magnetic moment of an individual free electron, which when we apply an external magnetic field acquires an energy, magnetic energy, which is this magnetic moment times so, and we know that in a magnetic field an electron has two orientations which are parallel and anti-parallel to the field, which are given by the spin magnetic quantum number -half and +half. So, we have corresponding to the two different configurations, the magnetic energy turns out to be plus or minus mu b p. So, when an external magnetic field is applied, the energy of the electrons with spin quantum number -half will decrease by an amount mu b b, while the energy of the electrons whose spin quantum number is +half will increase by the same amount mu b b. So, this is what we show in this figure. So, we just plot E versus K, but we conveniently split the band into 2. So, this is 0. So, positive case we have a parabolic energy dependence as we know already, and this is so on both sides. So, these are the 2 spin sub bands corresponding to ms equal to minus half and plus half. So, now this the ones with anti-parallel orientation will go up in energy now, while those with parallel orientation will go down in energy. So, that will be the situation. So, these will be the new configurations corresponding to parallel and anti-parallel. Anti-parallel spins, and these are parallel spins. This is the sub band corresponding to parallel spins. So, that would be the situation, and the amount by which this change takes place is what we wrote as mu b b. So, this is the same as mu b b here. So, this is the situation in an external magnetic field. So, equilibrium will be attained so as to make the energies of the spin up and spin down band electrons equal at the Fermi level. So, this is what is shown in the next figure. So, we have a net magnetization because the density of states of the electrons dFE dE depends on, this is equal to 4 pi into 2 m by h cross square to the power 3 by 2 into e power half dE. So, if this is E minus mu b b or E plus mu b b, the density of states will be different. So, the consequence of this will be that the electron concentrations, if you consider the electron concentration in the spin up side band, that will be half integral in the presence of an applied magnetic field of strength B, the density of states will be given by this, and we have the factor half because only the 1/2 of the number of electrons will occupy one spin sub band. Similarly, n down or n anti-parallel spins will have half integral So, this is the concentrations are different because the density of states are different corresponding to different energies. So, because of that, where in the absence of the magnetic field the concentrations were equal, but now there is an unequal concentration, and therefore, we have a net difference, and which we can write as the difference between the two configurations. So, we have this net can easily be calculated, and that is given as so that would be the net difference in concentration, and this can be simplified for small values of the applied magnetic field. We can write this by using binomial theorem. So, expanding the square root using binomial theorem, we get this population difference, the final difference in populations is turns out to be so that would be the difference, and the corresponding magnetization is just this times mu b. This is nothing but. So, this magnetization due to the difference in orientation of the two sets of spins turns out to be times, well, we can do a simplification at this stage using the expression for the Fermi energy is so using this we finally arrive at the expression for the magnetization in the form and therefore, the susceptibility is just m by b. So, times b. So, this susceptibility turns out to be this 2 is not. And this is known as the Pauli paramagnetic system. After Pauli, who first determined this. So, this is a paramagnetic susceptibility as seen from the positive sign, and this has the magnitude of this kind. Now, the question is, this is the difference in electron concentration, this is the Bohr magneton, the square of the Bohr magneton, and this is the Fermi energy. Now, the question arises, can we experimentally observe this? Well, the answer is it is rather hard, because this is complicated by additional effects. This is masked by the overall diamagnetism of the ion cores in the metal lattice. Also, as you will see, there is another effect called Landau Diamagnetism, which we will consider presently. So, both these effects, the diamagnetism of the ion cores as well as the Landau diamagnetic susceptibility, complicate, add to this, and therefore, the net susceptibility that one will observe in a metallic specimen is the resultant of all these three. So, but we already saw in the previous lecture on magnetic resonance, we talked about the NMR, nuclear magnetic resonance in a metal. We talked about the conduction electrons and their interaction, the hyperfine interaction between the conduction electrons which are in the S state and the nuclei. So, this provides the so called Fermi contact hyperfine interaction, which leads to the establishment of a local magnetic field which adds to the field applied in causing the resonance, and therefore, there is a shift which is known as the night shift. We discussed this in the lecture on magnetic resonance. Now, this night shift is also related to this Pauli paramagnetic susceptibility, and so both these effects are related. Now, we move on to discuss this other effect which is known as Landau diamagnetism. Now, what is this effect due to? This is, as the name implies, this is due to the not the spin angular momentum, but the orbital motion. Of the electron in a magnetic field. And when we say electron, we mean the conduction electron, not the orbital electrons, but the conduction electron which is free. So, when you apply a magnetic field, we usually write B equal to del cross A, where A is the vector potential, magnetic vector potential. So, if we apply a uniform magnetic field along the Z component, then this can correspond to a vector potential which has the components. So, in the presence of such a vector potential, we can write the Schrodinger equation for the electron, which is d square by dx square plus d square by dz square psi plus d by dy minus IEB x by h cross square operating on psi plus 2m by h cross square equals 0. That would be the Schrodinger equation, which has this additional term due to the magnetic field. So, we have to solve this by the method of separation of variables to obtain the energy eigenvalues in the stationary state. So, following the method of separation of variables, we know that these two parts correspond to the free electron. Therefore, we can write times u of x, because there is an x dependent term. So, the x part of the wave function will not have the free electron form, and so this u of x is the function corresponding to the x part of the wave function. The y and z parts are free electron wave functions, as in the case of the free electron in the absence of the magnetic field. So, substituting this back here, we can write the equation which is satisfied by the function u here, That would be the equation satisfied by the function u, where E prime is E minus h cross square k z square by 2m. Now, we define two quantities, the cyclotron frequency with which we are already familiar, omega equals Eb by m, and we also define x 0 as h cross by Eb into ky. With these two substitutions, this equation can be simplified to the following form. The Schrodinger equation, it turns out that the equation is identical to that of a displaced harmonic oscillator. Of mass m, charge E, angular frequency omega, and displaced by an amount x naught. Which is defined there. So, the energy eigenvalues of such a displaced simple harmonic oscillator are well known from quantum mechanics. They are given by where n is an integer. Say 0, 1, 2, etc. So that the total energy eigenvalue for such an electron orbiting around in the presence of an magnetic field turns out to be where E prime is E n given above. So, what is the result of all this? The motion now is of the free electron or the conduction electron, which originally had a plane wave like states in all the three directions. It means that they are free electron states, and now because of the application of the magnetic field, nu is. So, this omega depends on the magnetic field. So, because of the applied magnetic field, the energy levels only along the z direction are free electron plane wave like, while the energy levels in the other plane, the perpendicular to the z axis, the direction of the field direction, are quantized in units of the cyclotron frequency omega, h cross omega to be precise. So, this means that we have these energy levels are known as Landau levels, because Landau first described them. The result of this is that now we have to add the Zeeman term, well known Zeeman term, to this and find its effect. So, we can, the usual procedure is to calculate the free energy in terms of the partition function. Once we know the energy levels eigenvalues, we can write the partition function and so calculate the free energy, and then the magnetization can be calculated from the free energy as the first derivative of the magnet with respect to the magnetic field. So, the magnetization can be calculated. The calculation of this, the algebra is somewhat complicated. I will not go through it here. I will simply give the result of this calculation. It turns out that this magnetization corresponds to a susceptibility which is of the form chi p plus chi L. Here chi p is the Pauli spin susceptibility which we already discussed, and chi L is the Landau diamagnetic susceptibility. It is found to have a value minus half n mu b square by E f. So, the Landau diamagnetic susceptibility, the magnitude is just 1/3. The Pauli susceptibility is 3/2 with a positive sign. So, this is equal to 1/3 of chi p. So, the Landau susceptibility has a magnitude which is just 1/3 of the Pauli susceptibility. So, this is comparable to the Pauli spin susceptibility. In addition, it is also found that the susceptibility has an oscillatory component and which has a period which is given by delta 1 by b equal to so that is the period of these oscillations. These susceptibility oscillations are known as de Haas Van Alphen oscillations. This is an effect which was discussed discovered by de Haas and Van Alphen, so it has been named after them. So, this gives you the effect is that of an oscillatory susceptibility. This has a very important consequence that one can determine the topology of the Fermi surface using this, because the exact calculation gives delta 1 by b as 4 pi square mod E divided by h cross A. This is this A effective is the effective cross sectional area of the Fermi surface. So, the period of these oscillations is related to this cross sectional area, and therefore, determining this period as a function of the applied magnetic field gives us information about the topology of the Fermi surface. So, this is an extremely interesting effect which helps us in determining the exact topology of the Fermi surface in a real metal. The next figure shows the experimental recording of such quantum oscillations in the susceptibility of a sample of gold as a function of magnetic field strength. So, these are interesting experimental results associated with conduction electron magnetism. In metals. This also leads to a similar interesting effect due to the cooperative magnetic ordering of conduction electrons in a metal and leads to what is known as the band magnetism. We will discuss this in a separately.